In the field of wind turbine maintenance, artificial intelligence represents a transformative tool. In this video, we'll focus on a multi-agent AI capable of continuous learning and improvement. This capability is critical to its long-term value. Truly valuable artificial intelligence is not a static entity. Rather, it must constantly evolve and adapt to the organization's own operations or circumstances. This evolution ensures its relevance and effectiveness in a changing environment. Adaptation is key. AI must assimilate new data, respond to operational changes, and learn from real-world experiences. Only then can it maintain its accuracy and usefulness over time. The central component that enables this evolution is the continuous learning agent. This agent is the engine of the system's constant improvement. The role of the continuous learning agent is to ensure the accuracy, adaptability, and value content of the AI system. Its function is vital for AI to not only work today, but to continuously improve tomorrow or next year. The AI improvement process should be viewed as a feedback loop. This cycle comprises 4 interconnected stages: prediction, action, validation, and learning. Each phase contributes to the improvement of the system. For example, the AI could generate an alert indicating a possible bearing failure in the next 10 days. This anticipation is based on the analysis of complex historical data patterns. Based on this prediction, technicians execute the action. They assess the situation, make the necessary interventions, and meticulously document each step of the process. Human intervention is crucial and vital at this stage. Validation then takes place. The system compares the initial prediction issued by the AI with the actual result observed in the field. This comparison is essential to determining the prediction's accuracy. Finally, the learning phase closes the cycle. The fusion of the prediction and the actual result fuels the improvement of the AI's internal models. This process of continuous AI improvement means that, as it receives this feedback, it begins to produce much more accurate results. The continuous learning agent plays critical roles in the evolution of AI. One of its main responsibilities is detecting the accuracy of the system's predictions. It analyzes which ones were accurate and which ones were inaccurate. Additionally, this agent is responsible for collecting new data from a variety of sources. This includes information from SCADA systems, condition monitoring systems, CMS, maintenance logs, and even audio recordings of technicians. The diversity of this data can enhance this learning process. A vital function of the agent is identifying previously unseen patterns. It uncovers relationships and trends in the data that initial models hadn't considered. This allows for a deeper understanding of wind turbine behavior. The agent also autonomously adjusts and validates predictive models. It uses new information to optimize existing algorithms and ensure their relevance. This process is continuous and dynamic. Finally, this agent constantly monitors the system's accuracy and reliability. It continuously assesses the reliability of the entire system, ensuring that the artificial intelligence maintains a high level of performance and confidence. To achieve living intelligence in the AI system, several specialized subagents operate. These components work together to ensure adaptability and continuous improvement. These relationships are critical to the system's robustness. The predictive model trainer subagent is fundamental to the system's evolution. Its main function is to efficiently process large volumes of new data. This includes operational, sensor, and maintenance information. From this data, the subagent creates updated versions of the prediction models. These models cover wind turbine faults, performance, and behavior. The ability to generate updated models is vital. An advanced feature is its ability to autonomously tune model hyperparameters. This tuning optimizes the performance of each model without manual intervention. Automation accelerates the improvement process. This subagent also manages various types of predictive models. Its architecture allows for the integration and optimization of different algorithmic approaches. This flexibility is crucial for addressing data complexity. Examples of model types it handles include time series models, such as LSTM and Profit. It also includes classification and anomaly detection models, such as random forest and XGBoost. For regression, it uses remaining useful life or ARUL models. A real-world example of its impact was observed after analyzing 20 events across 6 Siemens turbines. The model automatically adjusted its sensitivity to the horizontal vibration pattern in gearboxes. This occurred on equipment with more than 30,000 operating hours, demonstrating its contextual learning capabilities. The accuracy and retraining evaluator subagent is crucial to maintaining system quality. Its main task is to continuously monitor the performance of existing models. This ensures that their effectiveness does not deteriorate. To evaluate performance, it uses advanced metrics such as area under the curve, AUC, F1 score, and accuracy. These metrics allow for identifying any signs of degradation in the model's predictive ability. Early detection is key. Based on these evaluations, the subagent decides when and how a model should be retrained. This decision is autonomous and based on the need to maintain accuracy. Automating this process is a major step forward. You can trigger local updates for minor adjustments or more extensive cloud-based retraining. The choice depends on the severity of the detected problem. This flexibility ensures an appropriate response to each situation. This subagent ensures that the AI not only learns, but also maintains its sharpness. Its role is vital for the system to adapt to new conditions and remain a reliable tool. Continuous improvement is its goal. The impact of continuous learning manifests itself in tangible improvements in AI performance. These examples illustrate how system adaptability translates into concrete operational benefits. Theory becomes practice. A significant case study is the reduction of false positives in condition monitoring systems, or CMS. This achievement was achieved by retraining the model with verified events. Real-world feedback was crucial. The model learned to differentiate between transient vibrations and those indicating a critical condition. This discernment ability dramatically improved the reliability of alerts. Accuracy increased significantly. The result was a significant decrease in the number of false alarms. This not only optimized maintenance resources, but also improved confidence in the AI's predictions. Predictive accuracy increased considerably. Another relevant example is the system's adaptation to changing wind conditions. The structural fatigue prediction model was retrained to incorporate this new reality. The AI demonstrated its flexibility. The new data included information on increased turbulence due to variations in the wind regime. This information allowed the model to adjust its stress and fatigue calculations. Accuracy in dynamic environments improved. This retraining ensured that structural fatigue predictions remained accurate. Even under changing environmental conditions, the system continued to provide reliable information. Adaptability is a competitive advantage. The importance of continuous learning is critical to the future of AI-driven maintenance. Without this capability, AI models quickly become obsolete. They lose their value and accuracy over time. A static system cannot adapt to new operational realities. It cannot incorporate new technologies or respond to changes in asset behavior. Its usefulness progressively degrades. With continuous learning, the AI system constantly improves. It adapts to the introduction of new turbines, evolving technologies, and changes in operating environments. Its value increases with each communication the AI makes. The result is an artificial intelligence that becomes a living system. It is customized for each wind farm specifically, learning from its unique and specific data. It incorporates the experience of its technicians and the particular operational challenges. This living AI is a dynamic tool that evolves with the operation. It is not just a technological solution, but an intelligent partner that grows and adapts. Its capacity for continuous improvement is its greatest strength. In this video, we explored how continuous learning artificial intelligence transforms wind turbine maintenance. We saw how the continuous learning agent and its subagents enable the AI to evolve. This evolution ensures its accuracy and long-term relevance. Every time AI gets it right, it improves. Every time it makes a mistake, it also learns from those mistakes. That's the true power of an intelligent system. Its ability to self-correct and adapt is what makes it invaluable. Now that we understand how an AI decides, explains itself, and learns, a fundamental question arises. How do we begin to implement all of this in the real world? Theory must be translated into action. In the next video, we'll address precisely this question. We'll focus on implementing the AI system through a pilot project. We'll explain how to begin this journey step by step. We invite you to join us as we explore the practical application of advanced artificial intelligence.